Hi everyone. We need to spend a little time working on 1.7 where we actually formally state some of the properties of definite integrals. I hope this section feels like a fairly painless, quick and easy clarification that we do. I think we've already been using some of these properties just intuitively. The ones that we haven't been, I hope that they still are really intuitive and just make a lot of sense by thinking about areas. But I would just make sure that you really commit to the idea that these are the rules for what you can do when you're manipulating integrals. Don't just assume that you can extrapolate from this and say things like, if I'm integrating a product, I'll just integrate the two separately and multiply. That doesn't work. So this list, I hope, is really easy. Don't overgeneralize and try and add to the list things that aren't really on it. Okay. So first property, and I gave us a function, a graph of a function, just so that we could have a visual, says that if you are integrating function f from a to c and then from c to b, you should be able to simplify this a little. So if we look at our graph, the integral from a to c, and I did pick a nice, easy, always positive function, but these do work even if your graph takes on negative values. So if we integrate from a to c, we're getting this area. If we integrate from c to b, we're getting this area. And if we're trying to simplify this statement, what I'm getting at is that we could say that's exactly the same as if we just went from a to b. So this is property number one. And with the picture looking the way I drew it, it's pretty easy. But I would point out that it actually applies to things that seem a little less obvious. So let's say we had this exact same shape, but now we had our A and our B and our C in this order. So now we're going to say if I go from A to C, this is actually me getting ahead of myself a little, I get this much area. Then if I go backwards from C to B, I've kind of double crossed that. And I'm going to say pause for a second on this because I actually need to talk about this a little bit before I get too carried away. Okay, so let's look at number two. Number two is really easy. Number two says if you integrate from A to A, so your upper and lower limits are the same, you don't get any area. And again, I hope that's really easy to believe. From A to A means you're really just getting a vertical line that does not have area. So always, it doesn't matter what A is, if you integrate from a value to the same value, you're not going to catch any area. Okay, three. This is the one that I need before I get too carried away with what I was drawing up at the top. If you go backwards, if you go from B to A, the problem is just that this is going to mess with the sign you're associating with your dx. So basically what we want to say is that integrating f of x from B to A should give you the exact opposite of what you'd get if you went from A to B. So if I have, let's see, I'll use all of this for now. If I have all of this area and I go this direction, I'm going to say the y values of my function are positive. So when I'm thinking about rectangles, each one has a positive width and a positive height. So I would expect this area to be positive. If I go this direction, my y values are still positive, so the heights of my rectangle are still positive, but now my delta x is less than 0, so here, greater than 0, f of x greater than 0, that means the area is positive. If we're going the other way, I still have f of x greater than 0, but now the delta x is less than 0, which means, again, area is positive, but the integral is going to count that as negative. It's going to say positive times negative is negative. So it just gives you the opposite sign. Don't confuse this and always assume that means that if you go from 3 back to 2, you're going to get a negative answer. The exception would, of course, be what if your function is already negative? So let's say this is from 0 to 3. So if we go from 0 to 3, the area is going to come out, or here, let's not say area, let's say the integral is going to be negative. If we go from 3 back to 0, now we have negative widths and negative height, so it'll actually make the integral positive. So again, the way I would say number 3 to myself is if you switch directions of integration, it changes the sign associated with the area. So it doesn't guarantee it's positive or negative, it just guarantees the opposite of what it would be if you went the right direction. Okay, so with that in mind, I can go back to this picture I started. So up towards the top, I said I was accumulating area from A to C. So in this picture, I'd have the integral from A to C is some positive number. When I go backwards from C to B, that's actually going to count that area as negative. So what's going to happen, here, let me just switch colors on this one, is where I shaded this in going back the other way, it's going to cancel out everything between B and C that I counted up the first time. So really you're only going to be left with the area between A and B, which is exactly what we claimed over here. I just think it's really cool to see that, well, it is really intuitive if C is in the middle of A and B. It is equally true if C is not in the middle of A and B. It still works. Okay, so number 4, I've made a picture down below because I always try and draw this and it looks terrible and it's never quite right. I don't know if the picture quite helps or not. But what I would say is, if you're trying to find the area under F plus G, so that's supposed to be this top one. What color am I on? Then you can think about the two functions separately. So let's say the line is f of x and the curve is g of x. So if you want to look at one of your rectangles, let's say it's this one. And let's just say we're doing left to make it easy. So we're focused on this y value right here. And what I want you to spot is that if we look at the area of this rectangle, so this is going to be, let's say this is 4.3 times 0.5. We could actually break that up into 2 separate rectangles. Let me see if I can snag a color. Ooh, maybe I can match what I had. Orange. Okay, so for this one, we had a rectangle right here that's about 1.6. So this is 1.6 by 0.5. And then, we need a gray one. This rectangle right here. Let me make my numbers work out carefully. What do I want? 4.3. I can't add right now. 7. 2.7. Oh my goodness. Sometimes I struggle when I'm trying to add. Okay. There we go. So now I made up numbers that even work. So I am estimating here, but the point that I want to get at is this big rectangle with the total height of approximately 4.3. You could picture that as just lifting the gray rectangle up and stacking it on top of the orange rectangle. So basically, if your function is f of x plus g of x, you could just think about that as taking, either way, this one I did the orange first, but over here I could do gray first. You could think of that as taking the y value on one of the functions, and then tacking on top of that the y value of the other function. So notice right here, this y value is 3. And all I've done is shift that up and stack it on top of my y value of 1.5. So if your function is the sum of 2 other functions, its area should be the sum of the 2 areas. I always feel like I get way tangled in this and I make it sound really hard. And then when I actually say my conclusion, people think it's really easy. But I would like you to get what the picture is saying. So what the property is going to say is that if we're adding or subtracting, I drew the picture for adding, but same idea, and we want the area under the sum of the 2 functions, we could just find the area under one function and the area under the other function and add them up. So adding functions just stacks the areas on top of each other. So it's perfectly legal, and I think we've even kind of mentally done this, to split up integrals, let's say plus or minus, over addition or subtraction. Okay, and then very last one, did I try and give myself a picture? I don't think I even tried, because I think I always make a mess. Says that if you have a function, let's say my function is this beauty that I keep drawing, and you vertically stretch or compress, flip can be in the mix as well, but it just makes this picture a little harder. So let's say we double all of our heights. So this is going to go about here, and this is going to go about here, this is going to go way up here. So same shape, but stretched vertically. So my y values all got twice as big, which means every single rectangle will be twice as tall if c is 2, which is what I'm imagining here. So the property is going to say that the area also goes up by a factor of c. So if your function is twice as tall, its area will be twice as big, which means you can just snag that c out in front of your integral. We've done this for indefinite integrals, antiderivatives all over the place, because we know when you take a derivative, the constant just sticks around, so when you take an antiderivative, the same should hold. And this is just looking at it in terms of definite integrals and thinking about it as area. So again, if the height of your rectangle doubles, pretend that's an exact doubling, the area of your rectangle has doubled, which means if your y values all go up by a factor of c, your area should go up by a factor of c. So these are your properties, and this section just gives you a little time to play around with these and make sure you really are good with them. So think about what exactly they're saying in terms of area, and hopefully that'll make them really easy to remember. Thanks for watching.